Hello everyone, I'm Anusha. I have just submitted my PhD thesis. My PhD supervisor is Professor Rilem. I work in the Department of Civil Engineering, IIT Madras, India. The topic for today's presentation is assessment of sustainability parameters for concrete systems with blended binders. If you look into the life cycle of concrete, there are different life cycle phases. The first phase is cradle, where the raw materials, cement, aggregates, are produced and extracted, later transported to a mixing plant where the concrete is manufactured. Later, this could be transported or placed through different technologies like 3D printing, precast, or the in situ could be used in order to construct a structure. Later, when the concrete is intact in the structure, it will be exposed to external environment during its service life. There could be repair maintenance phase to extend the service life. And at the end, the structure will be demolished where the waste materials will be disposed of, or it could be recycled to be used as a raw material again in the concrete production. In order to measure the sustainability, all the phases from cradle to cradle has to be analyzed. But most of the times, the systems from cradle to gate will be analyzed in order to calculate the embodied impacts, or this gate could be extended to the gate of a 3D printing or precast element factory or the construction site itself. And the systems like cradle to grave could also be used to improve the service life and the demolition deconstruction phase. Mostly, the recycle phase or the recycling phase is assessed separately in order to measure the overall recyclable potential of the concrete systems. So if you look into the embodied impacts of concrete or of a structure, majority of the impact comes from the construction and maintenance phase. If you look into one building, around 30 to 40% of the impacts is because of the concrete production. In 1 meter cube of concrete, around 60 to 80% of the impacts, it is due to the cement production. If you look into cement production itself, majority of the impacts is in terms of CO2 emissions and energy consumed. Around 80% to 90% of the emissions are CO2 because of the direct emissions from the limestone and from the fuels that is happening during clinker production. And energy consumed is because of the fuels that are being burnt in order to clinkerization in the clinkerization process. And it is also because of the electricity that is consumed during the different processes. Cement industry alone is responsible for around 5 to 8% of the global CO2, and it also consumes about 10% of the global energy. The critical aspects in cement production are the clinker content, the type and amount of fuels that are being consumed, the amount and the type of electricity that is being used in the cement production. So in order to reduce the embodied impacts of the cement production, there are several strategies that are being implemented. The strategies are like use of alternative fuels, use of raw materials, clinker substitution by SCMs, use of noble cements, reduction in transportation distance, etc. Here, life cycle assessment can be used as a tool in order to calculate the reduction or the change in the embodied impacts. For example, if we are using clinker substitution by SCMs, then it reduces the embodied impact, like it reduces CO2 emissions, use of waste materials will be included in the life cycle, there will be reduced landfilling. And there could also be improved performance in the later life cycle phases, like the strength could increase, the durability could increase. Because of durability, the service life also could be extended. Therefore, while conducting sustainability analysis of the concrete system, it is important that we consider the influence of the change in concrete system on the later life cycle phases also. So how did we come up with the sustainability assessment of the concrete system here in the present study? As a first phase, I conducted the life cycle assessment in order to calculate the environmental impacts that are associated with cement and concrete production for the Indian case. As a second phase, if these concrete has to be used in a structure which has different material properties like strength, durability, etc., then how to choose these concrete mixtures based on sustainability parameters, which can be defined through sustainability indices. As a first part of study, I conducted life cycle assessment based on ab initio framework. This framework was proposed to be used in cases where databases are not readily available, like India. This framework is based on the 4 steps, that is goal and scope, life cycle inventory analysis, impact assessment, and interpretation as defined by ISO. But the difference lies in the inventory analysis and the impact assessment. So in inventory analysis, instead of depending on the database, I went to different cement, aggregates, and concrete plants in and around India to collect the primary data. And instead of depending upon the default impact assessment methodologies, I came up with methodology to choose characterization based on each input for different cases. The first step was to define goal and scope. Our goal was to calculate the impact associated with cement and concrete production in terms of CO2 and energy for different case studies. And I choose different system boundaries like ground to gate to gate to check the influence of different processes on the total impacts calculated. The functional units were varying depending on the type of materials that were chosen. Like I calculated the impacts per ton of clinker, which was chosen as an input for calculating the impacts per ton of cement. Later, I calculated the impacts per ton of aggregates, and I calculated the impacts per meter cube of concrete, taking input as cement and aggregates. The different technologies were selected based on the different materials which were used. For data collection, I had visited different cement plants. The primary data, such as raw materials, fuels, electricity, chemical composition, transportation mode, was collected directly from the cement plant. I also want to understand how much fuel was consumed in transporting the materials. So I did a survey with the truck drivers at the plant to understand how much fuel was consumed. I was dependent on GS map and Google map for the total transportation distances. Then in case of ground to gate system boundaries, I was also dependent on the EcoInvent database to collect the data. How did I go about doing this? I floated the questionnaire beforehand so that the cement plant officials know what kind of data that I'll be expecting from them once I visit. Then I visited the plant, went in and around the cement plant to understand what are the different processes to have a process flow map. Later, I spoke to officials so that I gather all the required information for conducting life cycle assessment. For collecting the data for cement and clinker production to have a database of, I've been to around 6 cement plants in and around India, where 4 are integrated cement plants, where the clinker and cement are produced in the same plant. Then I also visited 2 grinding units where the clinker was being bought from a different cement plant and ground fine in these plants to get the cement. All the discussions and the numbers I am showing here today in the present study will be based on the Nandyal case study. The third step is impact assessment, where I choose specific characterization and conversion factors based on each input for different case studies. These characterization factors will help me to convert the input data into specific impact, that is CO2 and energy. Once I go to the cement plant, I collect the fuel samples from the cement plant in order to understand the chemical composition and come up with a CO2 characterization factor. If that is not possible, then I was dependent on the other databases for the characterization factor. Similarly, I conducted bomb calorimetry to understand what is the calorific content. If that is not possible, then I was dependent on the other data sources for the characterization factors. For the data that I collected for the present framework, I assess the quality based on a pedigree matrix. Based on this, the data was considered to be very good with a total score less than 12. The next step was interpretation. Once I calculate the impacts, I compare it with different system boundaries or different cements in order to understand which is the process that is responsible for majority of the impacts. Here I have given the results per ton of clinker for both CO2 and energy consumed. We see that with the change in system boundary, the impacts are also changing. The change in system boundary, the impacts are reducing because in ground to gate, all the processes from ground to gate will be considered, whereas in gate to gate, only the process which are inside the gate of the cement plants were considered. We see that with the change in system boundary in terms of CO2, there is a reduction of about 9%. But in case of energy consumed, there is a reduction of about 30%. In case of CO2 emission, we see that majority of the impact is because of the direct conversion of CaCO3 to CO2. And secondly, it is because of the direct CO2 from the fuels which are being burned for the clinkerization process, and later it is because of the electricity and transportation process. In terms of energy consumed, majority of the impact is because of the fuels that are being burned for the clinkerization process, and then it is because of electricity and transportation distances. Before calculating the impact associated with the blended cements like PPC, that is Portland Barcelona cement with fly ash, PSC, that is Portland slag cement with GGPS, LC3, that is limestone calcined clay cement with the combination of calcined clay and limestone, I had to understand what are the impact associated with these SCMs or the secondary treatment that is given to these SCMs. So I had collected the data from one of the cement plant where they were producing GGBS from GPS, that is slag. So I calculated the impacts, that is because of the production of GGPS, that is the secondary treatment given to the slag to make it fine. I also calculated the impact associated with calcination process of clay, and I also calculated the impact associated with the secondary crushing that has to be given to the limestone, wherein it has to be used in LC3. In this study, the fly ash was considered to have zero impacts because it was a waste that is produced from the thermal power plant, and there was no secondary treatment required for the production of fly ash. This is one of the clays where cement was being produced, like OPC and PSC was being produced, and I assume that LC3 and PPC will also be produced in the same plant with few assumptions. We see that with the production of blended cements, that is PPC, PSC, and LC3 with lower clinker content, the CO2 emission and energy were reducing. The reduction in energy was about 22% and reduction in CO2 was about 35%. Later, I extended the same framework to calculate the impacts due to concrete production. I visited one of the concrete producing batching plant in Chennai. I had already visited a cement plant so that I know what are the impact associated with the cement. I had visited aggregate crushing unit. I knew what are the impact associated with the aggregate production. Then I calculated what are the impacts due to the concrete production also. For this, I assumed around 30 concrete systems with different SCMs like Class C fly ash, Class F fly ash, two different kinds of slag, and combination of slag and fly ash, and also LC3. I see that with the use of blended cement in manufacturing of concrete, the CO2 emissions and energy consumed also decreased per meter cube of concrete. The reduction was about 30 to 45% in terms of CO2 and about 12 to 30% in terms of energy consumed. The second part of the study was to combine durability, which is a concrete material parameter, which would influence the service life of the concrete system in the total life cycle of concrete. So if you look into the literature, there are several researchers who have tried to combine durability for the overall sustainability assessment. The service life and the global warming potential can be calculated separately and later combined, or the functional unit can be changed in order to include the durability in the sustainability assessment, or there could be a single index which can combine the different parameters for the assessment of sustainability of concrete systems, or there could be multi-criteria decision making for sustainability. In the present case, I use two sustainability indices. One is energy intensity index, the other is apathy index. The first is the energy intensity index, which is the ratio of energy consumed and the compressive strength. The energy consumed per meter cube of concrete is calculated based on the energy sources and the processes involved in the concrete production. And this energy intensity index is a combination of the embodied energy and the mechanical integrity through the compressive strength. This can also loosely indicate the cost and the clinker content. The energy intensity index of different concrete system with different blended binders was plotted against the compressive strength of the concrete systems. We say that with the increase in compressive strength, the energy intensity index is decreasing. The second indicator which was used was apathy index. Apathy index is the ratio of CO2 emissions per meter cube of concrete and service life parameter. Apathy stands for something which is neglected. So CO2 emissions and service life are the two indicators which are often neglected in specification and construction contracts. I defined apathy index for two exposure conditions, that is, one is chloride ingress and the other one is carbonation of concrete systems. Here, AI chlor was defined for the chloride ingress, which is the ratio of CO2 emissions per meter cube of concrete divided by F chlor, which is a service life parameter which is dependent on the DCM. AI carb was defined for carbonation, which is a ratio of CO2 emissions divided by F carb, but where F carb is a service life parameter, which is dependent on the carbonation rate. Here, the CO2 emissions were calculated based on life cycle assessment methodology, which were dependent on the raw materials processes involved in the concrete production. The DCL and the KCO2 were actually determined in the laboratory. Finally, I came up with a sustainability framework in order to choose the concrete system based on sustainability. Here, the apathy index was plotted in y-axis, EICS was plotted in x-axis. The concrete systems which are sustainable are the one which lies in the left bottom corner of this framework. Here we can see that the concrete system which are lying in the left corner are having lower apathy, means lower CO2 emissions per meter cube of concrete and higher durability. Also have lower EICS, means lower embodied energy consumed per meter cube of concrete and higher strength. We can see that these concrete systems are the ones with higher replacement levels of SCMs like 50% slag, LC3 systems, and combination of slag and fly ash. And for carbonation, AI carb was plotted in y-axis and EICS was plotted in x-axis. We see that the concrete systems are sustainable, are the ones with lower replacement levels of SCMs. So it was possible for us to combine the mechanical strength, durability, and the environmental parameters together to come up with a framework to measure the sustainability potential of the concrete systems. Moving on to the conclusions. Durability should be an integral part of the sustainability assessment for measuring for the structural concrete systems. A framework has been presented here to help choose sustainable concrete mixes that can satisfy the strength and the workability criteria. This framework is based on two indicators, that is energy intensity index and apathy index. The critical parameters considered for sustainability are the durability, lower binder content, and lower chemical content. I would like to thank the help from different cement, aggregate, and RMC plants who gave me data for conducting life cycle assessment studies. I would also like to thank the Eminence Research Initiative grant on a TLC2 project by IIT Madras. I would also like to thank the partial funding which was given by Swiss Agency for Development Cooperation through LC3 project. Thank you, everyone.